Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Emanuele Daddi with us today. Hey, Emanuele.
Thank you, Frank. Nice to see you.
Nice to see you. Where are you located at?
I'm in my office, actually.
Which is where?
Late evening, and in the suburbs of Paris.
Paris, okay.
I work at Paris-Saclay, so in France.
Okay. Has spring started yet? Do all the trees have little buds coming out yet?
Yeah, actually, we got some early warm weather here, and actually the trees were starting to blossom.
Cool.
But then now it's really cold.
Oh no!
So we got sort of perturbation coming from the pole, and we had freezing temperature for a few days. But well,
it'll come. It'll
get nice weather will come back soon, hopefully.
It'll get there. It is April 4th of 2022 as we do this recording, and I'm in Phoenix. I do have grapevines. I do grow grapes, and I have them mainly against my my wall over there. And they're all throwing out their new leaves, and they're starting to get the little bud things going. So probably in about 2-3 months, I'll have some nice little red grapes to eat. So it's great.
Excellent.
I haven't made wine out of it yet, so that's a skill set I still have to do. But the grapes are cool.
Yeah, I'm also enjoying gardening once in a while, but tendentially I like more to observe than actually to work on it.
Okay. Plant, go. Yes. Very cool. Very cool. Well, it's all lovely. It's all relaxing. So it's very nice. Very nice. Emanuele, what do you like to do for research?
I'm an observer, as I just said. And so I like to work with many kinds of data. So through my career, I've been spanning a little bit the electromagnetic range from optical, near infrared, but also far infrared, and radio, and various kinds of things. I love work with ALMA also in recent times. So I try to put together multi-wavelength information to have better understanding of processes related to galaxy formation and evolution. That's really my main interest.
Cool. Very cool. And that is going to bring us to this very lovely APJ letter. It's open access, people. You can go get it for free. Evidence for cold stream to hot accretion transition as traced by Lyman alpha emission from groups and clusters at Z between 2 and 3.3. And Emanuele, take us away.
Yes, absolutely. So first of all, thanks a lot for having me and asking me to present this work, which is an APJ letter. So as people are aware, this is sort of short and limited in focus to sort of one key result or one key idea that then is developed to some extent with related implications. So the subject here deals with, again, observations that we're saying coming from Keck, KCWI, a new integral field spectrograph that was installed 4 or 5 years ago. And we have been using with this group of people that you can see here, with many of which we have actually been studying since about a decade, different high redshift groups and clusters beyond redshift 2, which is a little bit of the frontier because they are very difficult and distant and difficult to study. Where at the same time, they are also a little bit dangerous because, I mean, we don't have all the high quality information that one would desire. So we have to live with the kind of information we have.
Cool, cool.
So the key result that we thought to present in this letter was dealing with problems related to accretion. And notably, we have been using Lyman alpha observations as revealed by KCWI to try to say something about the phenomenon of accretion into massive halos in a distant universe, particularly because that's an open issue. So we have an underlying theory that describes how particularly cold material is expected to flow to these massive halos as a function of cosmic time. Excuse me. And I think I will get to introduce the theory when we arrive at speaking about figure 2 down the line. But before going there, I perhaps wanted to mention, as a sake of introduction that was mainly describing the theory, how this business of understanding accretion is crucial, particularly for galaxy formation and evolution. Mm-hmm. Say something or?
No, good, I'm good.
Because, okay, sorry. Basically, galaxies use cold gas to form stars. So the way how galaxies they are fed within their dark matter halos is important to connect to their star formation activity through cosmic time and give reason of when and how they're actually forming stars and converting this cold material into new stars. Mm-hmm. And basically the situation since about 15 years that the theory was laid out as to in which parameter space you can expect to have this cold accretion or not. Mm-hmm. There haven't been much advances from the point of view of the observations. Actually, from the point of view of theory, there have been a lot of work and many papers published advancing the understanding from the theoretical point of view quite in detail. Mm. But unfortunately, things have proved to be more complicated from the point of view of the observations, because in practice, observing accretion is difficult because accretion is thought to be beamed. So, you cannot easily detect it in absorption along many line of sight. And basically, again, from theory, the suggestion have been through the years consistently that the best way to directly unveil this accreting material, which is cold, would be through Lyman alpha emission. So this has been a concrete prediction since years, but the complicating factor is that it's not always easy to interpret Lyman alpha emission, which could come from this long sought after accretion, but could come from other sources and phenomena. So, this is clearly a difficulty in interpretation of the observation that we will get into for this letter as well. Cool. So given this suggestion from theory, we started up with a project following up basically a bunch of distant groups and clusters, those that were available and known basically once we have during this year. So maybe you can scroll down and go to page 2, where actually the groups and the sample of objects that we have studied is summarized in this table. As you can see, there are just 9. We provide coordinates, and the ratio will go from about 2 to about 3.3. Mm-hmm. And the table lists all the quantities that we have tried to our best of knowledge to estimate dark matter halo masses, Lyman alpha luminosity is coming from KCWI, star formation rate integrated over the structures, and AGN luminosities. Okay. So maybe you might want to show briefly figure 2, which shows the direction that, excuse me, I meant figure 1.
Figure 1.
Right there, the structure that,
let's do a global look first. If you want to zoom in, we can zoom in. So there's sort of a global of these.
Yes, so figure 1 is showing 8 of the overdensities that we have been observing with KCWI. Mm-hmm. So there is a 9th object in our sample, but we decided not to show in this work because there was another paper that was published last year, which was presenting in full detail that particular structure, ratio 2.9. So here, basically, we presented all the other Lyman alpha observations that were not presented before. So each of these panels showed a 3-color image centered on one of the overdensities. With, if you zoom, you might be able to see there is a dotted line that shows the field of view of the KCWI observations.
Mhm.
And then in the overlay is basically a Lyman alpha
Contour.
image. So it's where Lyman alpha is located.
Okay.
So actually, already a result of this paper is basically making the point that when we observe these distant groups and clusters, we basically always find a giant Lyman alpha halo. So you see the ruler showing 100 kiloparsec sites, for example, in this target. And so the Lyman alpha halos, they are of order of the scale. They vary a little bit among the targets. So we can basically detect giant Lyman alpha halo in all of the structures in this redshift range, with the exception of one object that was at the top left. Yes, exactly that one, which turns out to be actually the lowest redshift, 1.98, and also the most massive. So it's a very massive structure. And the idea is that this is basically the most evolved, where the least activity is taking place in its center. And therefore, it makes sense that it's where we don't see Lyman alpha, but we will make sense of its upper limit on the Lyman alpha emission as we go through the paper.
Cool.
So if you go briefly back to page 1, maybe you don't even need to go there, but we were briefly describing the data sets. So the different groups and clusters that we have been studied. Some of them actually they have been studied since more than a decade. So we were just quoting what had been learned on those from the literature. Some others there were newly presented here with different selection methods. Particularly, we have been looking for some of those at radio over densities, because they pinpoint star-forming galaxies which are concentrated in a small region and therefore probably group or some kind of structure at high redshift. And we also included 2 Lyman alpha blobs that we observed with KCWI. So in that case, the selection was more directly on Lyman alpha, and a posteriori we went there and tried to understand what kind of hosting halo was at their position.
Right.
So we present the KCWI observations, and we discuss how we identify the ratio of the structure and of some of the galaxies that are within the structure. And also we go quickly, let's say, toward actually quite crucial estimates, particularly of the host halo masses. Being a letter, we didn't have too much time to go into the detail, despite the fact that it's quite a crucial measurement for this work. And so to make the story short, we try to use as much as possible when we can X-ray observation, in some case as the Sunyaev-Zeldovich decrement measurement for estimating the total dark matter halo mass. But at the same time, we also use the stellar mass content of the structure and convert that using average relations between stellar and dark matter halo mass in order to get an estimate of the hosting dark matter halo. Unfortunately, for some of the lower mass structures, we didn't have useful X-ray constraint. So we had to rely basically only on the stellar mass content as a proxy for the hosting dark matter halo. And we acknowledge that in that case, the uncertainty is substantially larger. And so then at the same time, in these groups and clusters, we try to get measurement of the integrated star formation rate. And that is easy because we have Herschel observations that by default have pretty large beam of order of like 30 arcsecond, like for Spire. And well, normally that's a problem when you're trying to study galaxy, but in this case, it has the advantage that we are getting really everything in the line of sight. So they provide quite reliable bolometric luminosities information, which can be converted into star formation rate integrated in the structure. And at the same time, we were trying to get estimates of the AGN luminosities in this structure. These by means of X-ray observations and also mid-infrared. Okay, so sorry that I was a bit long and boring on these things, but I had to introduce the measurements.
I think it was great.
And finally, thank you, Frank. So we can get to figure 2, actually, which is really the key figure of the paper where the result is coming. Maybe you can zoom off, because I would like to describe first figure, the left panel. Yes, thanks a lot.
Yep.
So here you see the dark matter halo mass, the halo mass as a function of redshift for our sample, which are the black circles, where the size of the circle is actually correlated with the Lyman alpha luminosity.
Okay.
And this figure, you see all these lines, horizontal and diagonal, which actually are basically taken from the seminal work of Avishai Dekel and Bill Boyne, 2006, which set sort of the theoretical understanding for the accretion I was speaking in the beginning of our conversation. Mm-hmm. So basically, as you can see here, there are labels which are defining different regimes. Basically, M shock, which is below the horizontal line. Well, M shock is the horizontal line, and if you are in a halo that is located below the horizontal line, the understanding is that you can have cold accretion go into the halo, because basically it's only at M shock that a strong enough shock develops around the halo that prevents cold material from flowing down. So above M shock, in principle, you have hot accretion. So the possibility for the cold material to enrich the galaxies inside the halo is reduced or basically canceled. However, this key novelty that came up 15 years ago is the region in the right top wedge, where you can have cold streams in hot media. Mm-hmm. And this basically can go until this diagonal line, which defines M stream, which is basically another transition which sets the new limit where actually up to which you can have cold accretion, because this new theory is suggesting that despite you are in massive halos where you have shocks at their interface, still at higher redshift you have these filaments that can be very narrow and dense, which are the streams, that they can enter the halo and access the galaxy and bring cold material to the galaxies. So this theory is actually quite important for galaxy formation and evolution, because as I was saying before, there is a connection between dark matter halo mass and the stellar mass. So the M shock transition is basically at 6 in 10 to the 11 solar masses. Mm-hmm. And that corresponds to galaxies with masses of order of 10 to the 10 solar masses. So if the M shock was all this story, this would imply that particularly you would expect very little activity like of star formation in more massive galaxies. But we have been knowing since a long time, or last 2 decades, that particularly at high redshift, there are a lot of very massive star forming galaxies. Actually, the majority of star forming galaxies at high mass, the majority of galaxies at the high mass center are forming. So this theory sort of came handy to explain this kind of observations and the understanding of the distribution of star formation in distant galaxies. However, as I was saying, from the observational point of view, there has been very little confirmation that actually, for example, this diagonal line that is M stream has an impact on any observable properties of galaxies, for example, or structures. So this gets to the very core of this work, because as you can see, the sample is spanning across that boundary. Yep. So what we try to do with this sample in hand is going to the data and try to see it actually the observables like Lyman alpha or other observables were sort of aware of the existence of this M stream boundary, therefore, in a way, confirming that it does play a role. So I'm not sure if it's clear. That's basically what I understand.
Yep, I get you. I'm with you.
Then maybe you can zoom out if you don't mind. And before going to this figure that contains actually the key results of this work, I wanted to go briefly to the formalism.
Yes, please.
And how we are actually, in as simple way as possible, modeling the thing. Maybe you can scroll a little bit farther down.
Equation 1.
Yes, where, so actually, you see equation 1 that is coming from theory, that basically is setting the amount of bar is the baryonic accretion rate that is expected from a given dark matter halo mass and as a function of redshift. So you have scaling, like linearly scaling with the dark matter halo mass, roughly, but also rapidly rising with redshift. Yeah. This is from fundamental physics. So it's the total accretion, first of all, in dark matter is computed onto dark matter halos, and then assuming a sort of standard share, cosmic share of baryons within dark matter, you can compute the baryon accretion rate. So it is quite well defined. There are various formulations, but they are not very different globally. But then how to relate to the observation. So the relation to the observation is basically equation 3 and 4. First of all, there is a distinction. The previous equation was defining bar, but now we care about bar cold, which is the fraction of the baryonic accretion rate that can remain cold and therefore fit galaxies. And in a way, before we look at this formulation, then equation 4 says that observables like Lyman alpha emission that can be directly powered by this cold accretion can be written as be basically proportional to this cold accretion via a constant, in this case C, that is basically either to determine by theory or by observation, or ideally by both and compared.
Absolutely.
So then the way that we are actually modeling the effect of the M stream transition is in equation 3. So you can see that basically we are saying that if the dark matter halo mass is below M stream, which is like in the right wedge corner, in the figure I was describing before, then the cold accretion is the wall accretion. Okay. Yes, so basically, well, you have cold streams in hot media.
Right. Okay.
So when you're there, all the accretion is cold. But when you go beyond the M stream transition, we are introducing this sort of modulation or reduction of the fraction of accretion that is cold. It goes with this power law, basically with an exponent alpha, ideally to be determined from the data. And basically the understanding is that if alpha were to be 0, so there would be no dependence at all on M stream, and therefore, in a way, basically the observations wouldn't care of the M stream transition. Right. And instead, if there is a well-determined alpha, it means that basically the properties vary according to where the galaxy, the halo is located with respect to the M stream transition, in a way confirming that it plays a role and therefore supporting theory.
Cool.
Okay, so with this introduction, I should say that, of course, this is quite simplified, and this sort of formalism is meant to reduce the number of parameters, which are basically 2, the exponent alpha and the constant. Yes. Because of course, we are dealing with a complicated process. There could be other variables, and the functional dependence might not be linear. But I mean, given that we are at the early phase of the exploration, we decided to keep the simplest possible approach.
Good.
Okay,
good.
So you can go to figure 2, right?
Okay, if you don't mind. Right, let's blow that one up. Bar, Lyman alpha.
Yes, where there is basically the key result of our work. Maybe you want to zoom a little bit.
Yeah, let me go right there.
So we can see everything. Okay, so on the y-axis, here there is the ratio between the observable, which is the Lyman alpha luminosity, and the total accretion rate as computed from theory based on our estimate of dark matter halo mass and redshift. So if you remember equation 3 before, this is basically equivalent to the bar cold, so the fraction of accretion that remains cold. And then in the x-axis, you see that there is the ratio between the M stream boundary, which is the diagonal line in the plot on the left, and the actual estimate of the dark matter halo mass of the structure we are looking at. And the red points are our observations. So when you are in the right side of the plot with respect to the vertical dotted line, it means that you are in the region where there are cold streams in hot media. So the halos, they are below the M stream boundary in the left figure. And when you go on the other side, vice versa, you are on the upper end. So all halos, they are more massive than M stream boundary.
Okay.
So, and the key result is that basically we see this sort of smooth decline, and the ratio, the y-axis is getting smaller and smaller as you move to the left. Basically telling that the fraction of accretion that remains cold decreases as the halo gets farther away from the M stream boundary.
Makes sense.
And so this is the key result, because it suggests that, well, at least the luminosity, the Lyman alpha luminosity of these halos appear to know about this M stream boundary. So it's a confirmation in a way that the theory seems to apply to some extent.
Very cool.
Now, of course, you can see that there's these big symbols in the plot, which are the error bars.
Yeah.
In the right-hand side, they're really large, because we have to acknowledge that we have large uncertainties in the estimate of dark matter halo mass. However, as you can see in the left-hand part of the plot, the error bar goes actually parallel to the line, which at the same time is a worry and a feature. A worry, because, I mean, if you were completely dominated by scatter,
oh yeah,
this would sort of define exactly the relation that we are finding. However, what helps us, well, let me say, on the other hand, basically, we are using the estimate of dark matter halos on both sides of the X and Y axis. That's why the error bars goes in on the diagonal. So it's sort of normal, marginalized on the dark matter halo mass, at least in this range, which is to some extent desirable because it's uncertain. But so the reason why we trust the result, it's because it turns out that this is the part of the plot where, in any case, the dark matter halo masses, their best estimates. Particularly as you go farther to the left, the more accurate they are. That's where we have X-ray observations and SZ observations, and particularly the single object that is an upper limit that I was mentioning earlier on is down there. And that's the single object with the best estimates, because it's the most massive, so that it's easier to measure everything. So that said, and with the caveat that I was mentioning, to the best of our knowledge, we conclude that there is evidence for this decrease as we go farther away from the M stream boundary. And we also give an estimate of the exponent alpha, which is of order of 1. And it's constrained at the level of 5 sigma, basically, despite the fact that we have a very small sample, but it's basically the decrease is quite significantly there. Okay, so I guess that was the key results, but then we can go to the other figures briefly, which discuss a few other aspects. And so if you go to figure 3, these two panels, they're basically identical to the one we were just looking at, except that instead of Lyman alpha luminosity, now we are looking at the integrated star formation rate from the halos, and on the right, the integrated bolometric luminosity. So for the moment, on these tracers, we don't have a very significant result, but still we thought that it was worth pointing out the situation, and particularly for in view of the future, because we think it would be particularly desirable to increase the sample and have a better handling of what's happening in these tracers. Also because this is bringing us to the interpretation issues of our result. So empirically, it's quite clear, it seems clear from the data that the Lyman alpha luminosity seems to know about this M stream transition. However, as I was saying in the beginning of this talk, it's not always easy to interpret the origin of Lyman alpha. So the underlying assumption would be that basically, if it follows accretion, then it must come from accretion. And the physical processes by which it can come from accretion, they're basically collision and hydro instabilities. They're basically happening when the cold gas streaming interact with the hot gas within the halos. However, we know that Lyman alpha can come from many other things, like it can come from photoionization from like other star-forming galaxies or AGNs within the halo.
Okay.
And therefore, looking at these other observables can sort of provide a confirmation that we are getting the interpretation not too wrong, let's say. Particularly the fact that the left plot here, the star formation rate, even if only at like 2.5 sigma, confirms that there is actually a decrease with a slope that is also not far from 1, actually consistent with the one within the uncertainty, sort of supports the idea that not only Lyman alpha is declining as you go to the left of the plot, but also the star formation rate is declining at the same time. The interesting thing is that there is a lot more scatter in the star formation rate than what we had seen in the Lyman alpha plot. And we speculate, or so we thought that this extra scatter is interesting. Although, again, this is a small sample, so we have to be careful when over-interpreting what we have. However, in the alternative interpretation that I was giving you, which is that, let's assume for an instant that Lyman alpha that we observed might actually come from photoionization and not from collision or hydro instability. In any case, the photoionization rate, whether they are from star formation rate or from the AGN, would indirectly come to the accretion in any case, because we understand that it's the accretion that is feeding the galaxies, which are forming stars and they're growing AGNs, and this might be helping the cold gas to shine. So in a way, what we say in this letter is that because we have a lot more scatter in the star formation rate, this favors the idea that Lyman alpha might come directly from this accretion process.
Yeah, that would be cool.
Of course, this is a suggestion and would need to be confirmed.
Cool.
And for the case of the AGNs, instead, there is even more scatter. That is understood because basically we know that on average, AGN and star formation, they go together. It's like if you do ensemble average, different kind of redshift or mass ranges, you more or less find always the same ratio. But the AGNs is understood to happen on a much shorter time scale of variability. So you can have this sort of average ratio only when you have large samples. When you're studying small sample, you do expect a large scatter in the AGN property. So this is sort of understood. And again, we decided to put the figure to show the situation and also in view of the future, because it would be, we believe, important to have a much larger sample and checking what the average AGN luminosity behavior in this diagram to support what we are finding. Okay, and then you might want to go to figure 4.
Surely. Back that off a little bit. Let's try that.
That's actually we made for the same kind of discussion of the interpretation of the Lyman alpha emission, because again we are trying to gather as much information as possible as to whether the Lyman alpha should be interpreted as coming directly from the accretion or coming indirectly, perhaps through photoionization.
Right.
So here we decided to compare particularly to samples of quasars, because there are a lot of very interesting observations that have been accumulated in the last 5 or 6 years of giant Lyman alpha nebulae around quasars in the distant universe. So there are these samples by Borisova and Mackenzie.
Yeah.
So what this figure is showing is, again, on the on the left, on the y-axis, there is Lyman alpha luminosity. And on the x-axis is the AGN ionizing photons rate. So basically what we are computing is the number of photons that are energetic enough to ionize hydrogen which would result therefore into recombination and Lyman alpha emission as a result.
Yeah.
So we have drawn, well, the red points are the quasars, and our sample, they are the black and the blue points. The blue points, they are derived based on the estimates of the integrated bolometric luminosities of the quasars, mainly coming from the mid-infrared and X-rays. Because all these AGNs, they are very obscure in the host galaxies. And to show the range, we are also showing the black points, which are coming directly from like the UV observations of these AGNs.
Oh, okay.
So of course, it's well understood that AGNs, they are not emitting symmetrically. So it's not unreasonable that in some directions, the host can be much weaker than what you calculate from like the bolometric luminosities. However, the particularly relevant observation that we thought to show here was that in our case, they're all obscures, basically. So there is a large difference between the bolometric luminosities and what we actually see statistically in the sample, which suggests that it goes online with the idea that these luminosities are not very high for typically AGNs. Obscuration might be more prevalent than like for bright quasars. Anyway, the important lines here are the diagonal lines, which are showing the ionization limit is basically the limit where you have a bright enough quasar that can account for all the photons that you see in Lyman alpha. This is the dotted line. Then you have the solid line, which is where the limit would get if you were to assume more realistically, like that the opening angle of your quasar is typically of order of 30%, so it's not on the 4 pi. And also that the escape fraction of ionizing radiation from the host is not 1, but like 30%, which is what I've been observing in some high redshift quasars, actually. So you see there are uncertainties and the line can move. But basically, the bottom line is that a fraction of our sample is actually too left to be accounted for by ionization. And then there is another fraction which is sort of intermediate, and still there can be some contamination, well, actually some contribution, let's say, from photoionization.
Yes.
So, I mean, we try to give as open an interpretation as possible without pushing too much. And the real thing is that we would need still to demonstrate really that the bulk of the emission is coming from accretion.
Yes.
And I mean, this is basically the situation with this sample. We would need more observation to actually conclude on this point that is nevertheless quite important. And so on the right plot, I just can describe briefly. Basically, we were trying to make the point conversely. If you use the scaling that we had derived from our finding, whether the quasars, they are bright enough or they're reasonably bright in Lyman alpha to be explained by accretion. And of course, the answer is that they are overluminous. So I mean, self-consistency check, because we know that they have the vast majority of their Lyman alpha emission is from photoionization. So we are trying to emphasize how we think they would behave differently in this parameter space. Okay, so I guess we are getting toward the end, and maybe we can just go to look at the next couple of equations that we thought to conclude the paper with, basically making the point based on our finding and the scaling that we are suggesting, where the fraction of accretion that remain cold declines with that power law with exponent 1. We basically can use these results and rewrite the equation in a way to suggest what kind of Lyman alpha luminosity can be expected from distant structures, which could be useful for the community in the case, for example, of the use of Lyman alpha observation to try to locate dark matter halos. But also we thought particularly interesting to discuss the behavior. So this slope with alpha of 1 implies that if you stay at fixed redshift, you basically expect a behavior where the Lyman alpha luminosity would increase linearly with dark matter halo until M stream. And this is equation 5. However, if you go beyond M stream, you have a curious behavior because the Lyman alpha at that point would remain constant. And this is due to this alpha 1, because basically the fraction of accretion that remain cold would be going down like 1 over dark matter halo mass, but the total accretion goes like proportional to dark matter halo mass. So it cancels out and you get a constant. So basically, actually one of the important, perhaps the most important results, apart from confirming prediction from theory, is this suggestion that the slowdown of accretion when you get into the hot accretion regime is not so fast. It's actually modulated in a way that the total amount of cold accretion remains constant, regardless of how far you are from M stream. So if this is true, has also implication for galaxies, because we basically suggest that you don't have such a thing as starvation, at least not within the range that we have been looking at, because cold accretion is never really shut down completely, even if you go quite farther away from this M stream boundary.
Okay.
Again, of course, this will need to be confirmed by future larger samples.
Indeed.
Okay, I think this is all I had for this paper.
Emanuele, thank you so much for walking us through your very lovely letter. And you hit on it a couple of times there about going forward. So let me ask, where do we go over the next 2 to 5 years? Are there already additional observations in the pipeline? Do they remain to be made? Are there other ways that we can get, let's say, X-ray data on some of these to help better constrain some of those larger ones? So just kind of where do we go over the next 2 to 5 years to nail down this transition?
Yeah, in principle, there could be many things to say, but one thing that actually got me very interested is what I was just telling you about the implication for the galaxies. In fact, in an earlier version of the paper, we were concluding with a short paragraph discussing the implication for the galaxies, but quite wisely, the referee told us that, that would require
a whole different ball of wax.
A whole different paper, basically. And that's what we decided to do. And actually, we have written another work that is detailing the implication for the galaxies. And so that's something that we're basically doing now, and which particularly interests me, because it also affects the understanding of quenching that has been a long lasting problem, because of course accretion is to explain star formation, but at the same time also lack of star formation, so the relation with to quenching. So this is one line of direction for future research. And of course, as I said multiple times, this letter was based on a very small sample, so we would like, and hopefully the community will also work toward, we'll present a larger sample soon. Our group has started an effort to try to confirm spectroscopically a larger sample. So I mean, this is something that takes quite some time. We have been applying our favorite selection methods, and then hopefully at some point in the future, we will be lucky enough to get observing time with keck to study this object, and hopefully have better statistics. It will take some time for sure. And then another important thing, as I was saying in the presentation, we would like to have more like physical diagnostics on the Lyman alpha emission. So looking at other transitions, constraining line ratios, which unfortunately we haven't done in detail yet. And ideally also comparing to simulations. To have an idea of like interpreting kinematics and other features, morphology, the simulation could be quite illuminating. And well, a little bit is starting in that direction also. But in terms of what you were suggesting, having better X-ray data, I'm afraid I will have to wait for the Athena mission or maybe other missions that are planned in the X-ray. So maybe a decade or more when there will be the sensitivity to actually do a much better job than we can do. And we hope when that will come that our estimates are not too off.
There you go. Well, there's a prediction. Cross your fingers. Cross your fingers. Very cool.
Exactly.
Very cool. Well, I look forward to seeing this. Look forward to the paper you're writing now on the implications for galaxy formation, and I'd love to see a sample 10 times larger, and so we'll see where that goes over the next couple of years. So very cool, Emanuele. Thank you so much.
Thank you very much, Frank, for your time.
Yeah, thank you. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye, everybody.